Hit record and we start the video with thank you, Rami.
Okay, it's recording.
Alrighty. I'm uploading this unedited, so I'm going to need to get started. Let me just pay the cameraman 50 math points.
Thank you.
Thank you, Rami. Let's get going. Now, if you don't have work to do, you might want to stay in here, but I don't think that Mr. Meltzer thinks that you're staying in here. He said, get me set up.
I can ask Morgan if he needs me to film something real quick.
You're welcome to come back, but I'm getting going. All right, everybody, this is the slide that we left off on. Transparency of a lake. So they are explaining that this model, this equation, is used to connect the intensity of light before and after going through a material. So essentially how dark it would be or how bright it would be at a different depth of a lake. But the trouble is that the two variables that we might be measuring are inside of the natural logarithm. So that might be a problem if I was trying to solve for I or solve for I0. And in the first part, k is a constant, x is the distance or could be the depth, and they're telling me solve for I. So I'm solving for the variable right here. And I know that I need to move over the other terms, the other factors and parts of the equation. So I'm going to rewrite. And I'm trying to isolate the logarithm first. I will do that by multiplying by negative k. I want to cancel this negative and this k. And I get ln of I0, or I over I0, equals negative kx, right? And then we know that this natural logarithm is really log base e, and we would use the inverse of any logarithm to cancel out, quote unquote, the logarithm. So I can raise this equation, or e to the power of both sides of this equation, and that would cancel out the natural logarithm, just like 7 to the power of log base 7 of something would also cancel out. That gives me, and forgive me, I don't have that much room on the board here, that gives me, once these cancel, I over I0 equals e to the negative kx. So on the left side, there's no more logarithm and there is no e. I've done that to cancel it out. Just like I would square a square root, and I would write what was inside. And that's equal to negative kx. So we're almost done. We need to solve for I. I would do that by multiplying by I0. Sometimes we call that I naught. It means the initial intensity of light. And there you go. I have I isolated, so that's part A. Okay, in part B, it says for a certain lake, k is equal to 0.025, meaning I could plug that in for k. It's a constant. And the light intensity, I0, is 14. That's measured in lumens. And they're asking me to find the intensity. I always got to go back to the definitions. So they're saying I0 is a number they gave me, and they're asking me for I, which is why we solved for I. Okay, so that just means plug everything into this equation. I is equal to I0, so that's 14 lumens, e to the negative k, 0.025, times x, which is 20. Only calculator I see is this TI30X, but that'll do. I believe we have e. Yes. All right, 14 times e to the negative 0.025 times 20, 8.49 lumens. And that's it. Moving on. Pause the video if you're confused. Rewind if you're confused. Solution, but we did that. We got 8.49. Compound interest is just reminding you of the formulas. We do need to know these formulas. They're on the quiz tomorrow as well. I will not be providing these formulas. I think that we should know them. So depending on the question, we will use a simple interest or compound or continuously compounded interest formula. But now, because we can solve for variables that are in the exponent, by using logarithms, we're going to be using these same equations, but not the way that we did in the first 3 topics of the chapter. A sum of $5,000 is invested, that is P0, or P. It's the principal at an interest rate of 5% per year. Find the time required for the money to double if the interest is compounded according to the following method. So that would mean, and I'll go back to this, we have A, P, and R, and we're solving for T. That would mean that P for both of these problems is equal to 5,000. And A is equal to, well, doubling that, 10,000. I want to remember to point something out about those two numbers. They did not actually need to give me a number that we originally had. It will take the same amount of time for any amount of money to double. But either way, I could plug these two numbers in. And we're finding the time required for the money to double if it's semi-annual. That means twice per year. So now I'm just going to plug into the equation P equals A equals P times 1 plus R over N to the NT. Everything that I know, 10,000 equals 5,000. 1 plus 5%, 0.05. Semi-annual, twice a year. That's N, and that's T. Right, so I've just plugged in all the corresponding variables. R, N in both places, P, and A. So again, I'm solving for T. This is an exponential equation, so the first goal is to isolate the exponential factor, or the exponential expression in the equation. So I'm dividing by 5,000 first, and I get 2. Well, that's no surprise. Like I said, this is arbitrary. Imagine, had I been given 7,000 instead of 5,000, this would be 14,000, but the next line of my equation would be the same. So sometimes we leave that off and people don't know what to do, and I say make up a number then to start with the amount of money. But you don't really need to. It's more important that at some point, this quantity, and I could just simplify that, 1.025 to the 2t. Right? So that's 1 plus 0.05 divided by 2. 1.025 to the 2p. So all I've done is divide by 5,000 and simplify. So again, now I'm solving for something which is in the exponent of the expression that I am looking at, and I have to use a logarithm. Now, this is not a log equation. I'm not raising any number to the power of both sides. I'm using a logarithm, which I'll write out. But we have to think, how do I cancel out a base of 1.025? Well, the only thing that cancels out a base is the logarithm with that exact base. So something we have not needed to do yet, and why you have that function on your calculator, is log base 1.025 of 2. We would not say to the 2 power. This number is too long to kind of write neatly, but keep in mind that that's underneath. I'm using parentheses to differentiate. It is not an exponent of 1.025. Again, we'd read this out loud as log base 1.025 of 2. And then on the right side, I'll write it out because we want to see that it cancels. I've taken the log of both sides, and the base is the same as the base of this exponent. These two cancel out, and we get log base 1.025 of 2 equals 2t. This is a number. If I would like, I could just calculate that number right now and then divide by 2. People were saying that yesterday. But also, I could divide by 2 and then plug in. And that's what I'll write down, but I want to know what that number is. 228.1. Okay. Just switching around the equation, log 1.025 of 2 divided by 2. So that's about 14 years then, eh? Divided by 2, 14.03. 14.03. It is years, right? Years. Should be good. Pause the video if you need to look at that for longer. You should be writing this down, I think. Again, I don't care if you do this tonight or tomorrow, but these are notes. I can't post these notes. I'm in a classroom where I don't have a stylus. I'm trying, but I figure it's still online, so it's all the same. Sorry about that. Okay, so there's a part B. I'm going to erase this. Continuous. Most of the things are the same. 10,000 equals, well, I'll write the equation that's relevant, sorry. A equals P e to the RT. Part. 10,000 equals 5,000 e to the 0.05 t. That is R, the same R as before. There's no n. It's not compounded a certain amount of times per year. It's continuous. Again, that is going to give me 2 after I divide. You did not need to be given the $5,000. The same question has the same answer without an amount of money at the beginning. But it does help to start with this so that you can see why we can get to 2 equals ln, getting ahead of myself, 2 equals e to the 0.05t. How do I solve for e in an equation like this? I have isolated the exponential expression. I take the natural log of both sides. That is log base e. But a shorter way to write it is natural log. ln of e is 1. Technically, this exponent would come in front, and this would just be ln of e, which is 1. And so we get ln of 2. In other words, it cancels out. 0.05t. I say that for future problems, which we're going to get to in a little bit. It does come in front. We wouldn't need to put it there because it's just canceling out like the previous problem and becoming just the exponent. Lastly, I solve by dividing by 0.05. T is equal to ln of 2 divided by 0.05. I think ln of 2, I think I know it, but we're going to check. 0.69, I thought so. 0.69 is ln of 2, so divided by 0.05 is times 20. That is 13.9. And that just conceptually goes back to the idea of, although you are compounding more often, you are compounding less money when you do that earlier in the year. So it does not gain you as much as you might think. It is diminishing returns, and we see that we only get slightly less time to double than it was at a semi-annual rate. Cool. $4,000, that's the final amount. If it's compounded continuously, $1,000 is initially invested. It's compounded at 4% per year. There you go. Got to speed up if we want to get through a lot. 4 equals e to the 0.04t. ln of 4 is going about the same way. Right? ln of 4 divided by 0.04 is 34.7 years. All right. Compounded daily, real quick, we'll do that. The annual percentage yield for an investment that compounded per year daily. We have the equation A equals P So here, we're comparing to the equation 1 plus r to the t. One plus r over n, 6%. We don't know this. We don't know this. And we want to know how many times per year. So if I compare these two expressions, I have p times 1 plus 0.06 over 365 to the 365. But knowing that this exponent came from multiplication, if I raise it to a power, I could separate those two exponents. I'm doing this so that I can have some quantity raised to the power of t, and that would be this quantity. So all that I need to do to solve for the value is to calculate what is inside of this parentheses, or what 1 plus r is. So I will do that. 1 plus 0.06 divided by 365, all raised to the 365th power. Yeah, that looks good. That is 1.0618 to the 10. In other words, what we're doing in a problem like this is rewriting it in a different form, using exponent rules to rewrite it in a different form. And that's really just factoring out a t and calculating the inside. So then working backwards to what r is, I'm essentially looking at just the decimal part. And we find that even though it says 6%, it's compounded at a rate of 6%. The annual yield, right, is a little bit of a different thing. It's how much you would get, how much more you would get by the end of the year. And since the amount you have in your account goes up every year, you actually end up getting a little bit more than 6% by the end of the year. And that's what we see, 6.18. All right, solve by equating exponents. What does that mean? Well, to give you a very simple example before we do that, 3 to the x plus 1 equals 3 to the 10th. I don't need to know anything about logarithms to know that the only solution here is to make these two numbers the same. So in other words, x plus 1 equals 10, x equals 9. And we could just imagine that by saying, what number can I plug in here that would make both sides the same? If I put a 9 for x, I'll get 3 to the 10th, which is equal to 3 to the 10th. So in a situation where you have the same base and one base on each side, you can equate the exponents because it's the same thing as when we raise both sides to the power of, we raise a number to the power of both sides. But that's not where we're starting right here. We don't have a common base because here's a 4 and here's a 1/2. But I know that both 4 and 1/2 are powers of 2 and can be written as such. So I can rewrite this 4 right here as 2 to the 2nd. And that is raised to the x. I'm keeping the exponent the same. And then I can write 1/2 as 2 to the -1st power. And that is raised to the same exponent, x minus 3. So I've essentially substituted for 1/2 and for 4. Then I can use exponent rules to rewrite this, both as a power of 2. And this is -1 multiplied by x minus 3. So that becomes -x plus 3, because I have a power to a power. But at this point I have the same base. So 2x is equal to -x plus 3. 3x equals 3, and x equals 1. You could plug it back in. 4 to the 1 is 4. And 1/2 to the 1 minus 3, that's 1/2 to the -2nd power. That means flip it over and square it, and I get 4 both ways. So that's the solution. You want to try to do that before you try to do logs, because I personally think it's much simpler, and it wouldn't be necessary to introduce a logarithm in this problem. All right, so a few of these. I've already kind of explained the idea, so I'm just going to try to think out loud. We have 3 squared for 9, all raised to the 2x. And we have 3 to the 3rd. Helpful to know your powers. I know this is a power of 3. Sometimes I have to go to a lower number to the x minus 1. So 4x, 3 to the 4x, is equal to 3 to the 3x minus 3. But 4x is equal to 3x minus 3. X equals negative 3. 100 is 10 squared to the 7x plus 1. 1,000 is 10 to the third. It's the number of zeros that it has, minus 2. 10 to the 14x plus 2 equals 10 to the 9x minus 6. 14x plus 2 equals 9x minus 6. Five x equals negative 8. X equals negative 8 over 5. Doesn't have to be a nice whole number. Let me just make sure. That's 10 squared, 14x plus 2, 10 to the 9x minus 6, 14x plus 2 equals 9x minus 6, 5x, and negative 8. Negative 8 over 5. A little harder to check that, I admit. You can't just plug it back in and check as easily. All right, 81 is 3 to the 4th, because 3 to the 3rd is 27, so it's got to be the next one. 3 minus x. 1/3 is 3 to the negative 1st, 5x minus 6. 3 to the 12 minus 4x equals 3 to the negative 5x plus 6. 12 minus 4x equals negative 5x plus 6. On the left side, I could get an x and then subtract over the 12 and get negative 6. Pause the video if that's too fast. I think you can play this on 0.25 speed or something like that, maybe half speed. I got a lot to do. What can I say? All right. So now I can't get 5 as a power of 2, and I shouldn't try. This goes back to what we were talking about yesterday. If I take the log base 2 of both sides of this equation, then these two will cancel, and I get x equals log base 2 of 5, and that's a number. That's exact form. Sometimes I don't mind if you just write it that way, but if you needed a decimal answer, you would type that into your calculator, which I'm doing. Well, I'm not typing it into your calculator. 2.32. All right, same deal.
Lopez, if you're in the building, report to the gym immediately.
Log base 7 to cancel that out, cancels out the 7. 9x equals log base 7 of 15. Divide by 9. Log base 7 of 15. Divided by 9 is 0.155. In general, the rule with rounding right now is just don't round till the final answer, and give me enough decimals that I can tell what the number is. Don't make this 0 or something like that. Okay. 4e to the negative 0.3x equals 20. I'm trying to isolate the exponential expression right now. E equals negative 0.3x equals 5. Negative 0.3x equals ln of 5. I want to always show that step. I've taken the natural log of both sides, canceled out, ln of 5. X equals ln of 5 divided by 0.3, negative 0.3. ln of 5 divided by 0.3, negative 5.36. Good. All right, solve a logarithmic equation. We've got logs on both sides. It's actually just like the exponential equation once you have a common base. You could have never heard of the logarithm before and not known what function it is. But you will notice that the same function is on both sides. The log of something equals the same log of something else. Well, they both would need to be the same thing. Technically, I could say I'm raising 5 to the power of both sides. But at the end of the day, as long as you have the same base, it should make sense to you that you would equate the two arguments. You might have seen that on your calculator. Invalid argument. The argument is what is inside of the logarithm, but it's actually what's inside of any function, the argument of a function. 4x minus 7 equals x plus 5. I will leave that as an exercise to the class. You can solve for x there. All right, now I don't have a log on both sides, so I can't necessarily use that, so that's why I brought that up. To cancel out the log, since I need to solve for x, I need to raise 4 to the power of both sides of this equation. So now those logs, that log and 4 cancel. I get 5x minus 1 equals 4 to the third. 5x minus 1 equals 64. 5x equals 65. X equals 13. Not so bad. It's just like squaring both sides of an equation once you've isolated the radical. I've isolated the log, and I don't square or raise to the fourth. I raise 4 to the power of that side, and it will cancel out the logarithm. Oh yeah, okay. So we're using an exponential model, but we're rewriting it like we did in that investment problem before. So I have y equals 100, 1.08 to the t. But they want to know the monthly increase. So that would mean that I need an equation where instead of t, I need the monthly amount of months to be the variable that I'm plugging in. And so it's true that the number of months is equal to 12t. It took me a second to think about that. You see that? M is equal to 12t. So in other words, t is equal to m over 12. That makes sense. If it's been 24 months, it's been 2 years. So now I'll just make a substitution here. This is something you'd want to do if you're changing from a monthly to a yearly rate or vice versa. Anytime, make this substitution over here, m over 12. Now the monthly rate of increase is going to be, again, what 1 plus r would be. What 1 plus r would be if we were raising it to the m power. Again, we're trying to compare to the equation a equals p, 1 plus r to the t. Now t stands for time, and sometimes it is in months, but maybe I'll just write it as m. Right now, this is not just an m. So I need to separate this exponent. And I'll use another pair of parentheses. M over 12 is the same thing as m times 1 over 12. So your goal is to get a singular variable to be this exponent in the top right. And to do that, I'd need to factor it out and leave behind 1.08 to the 1/12. If I calculate that, I'll notice in the equation that it's equivalent to 1 plus r. And so I'm just going to do 1.08 to the power of 1/12. And it should be less. If it's going up 8% per year, then every month it's going up less than 8%. That would make sense. 1.006. Looking at this, I know that that is 0.6%. 1 plus r, I could subtract 1 and then multiply by 100, and that's what I would get. Same strategy. The number of weeks is 52 times the number of years. And that would mean that P is equal to P0, 1.46 to the, well, T is equal to W over 52. Oh, yeah. Okay. I want to show you it this way. We're good. I'll put the W back, but I think it's easier to see the numbers this way. So that means I need to do 1.46 to the 1 over 52. That's 1.0073. This would depend on what they gave me in the multiple choice. I still think it makes sense. To start out with that substitution to get the 1 over 52 out of it, 0073 to the W. I might have looked for that. I think it's a more useful equation if I want to know per week. But what we notice in the answer choices is they all still have 52t. Now that's okay, because W is equal to 52t. So by comparison, I see that A is correct. This formula would be true if I wanted to know after a certain amount of weeks. But if I still want to know after a certain amount of years, I would multiply that number by 52. If I'm compounding 52 times and ending up with an increase in 46%, I would need to take the 52nd root of that to find how much I increased per singular time. All right, great. Common base? No. But then what base should I take? If I do log base 5, I would cancel out the 5 here and get x equals. But log base 5 there won't cancel that out. So let's try that. Log base 5. Log base 5. Well, that cancels out. Like I said, x equals. Here, can't cancel this out. However, the exponent rule for logarithms says that an exponent can become a coefficient. One thing you really need to keep in mind is that once you have no variable in your logarithm, that is a number. Log base 5 of 4, log base 5 of 4 is 0.861. And this is now just a regular algebra equation. I don't like to round, and I'm not going to use this decimal as I do my algebra. I don't like to round in the middle of my algebra. But I want you to see it that way, because the next thing I'm going to do here is distribute. And I'm really distributing this number. So this is just to help you visualize. X equals x times log base 4, the log base 5 of 4, plus log base 5 of 4, which really is standing in for 0.861. Now I have still two variables, so I can do x minus x log base 5, trying to combine like terms, but it's a little bit different here. Right, from the very beginning, I've taken the log base, one of them. I could have done this with the 4, actually. Could have done this with the 4. It wouldn't have made a difference. I canceled out that base. And then, on the right side, I took this exponent and put it in front. Because this is a number, I could distribute that number. And that's what I've done, again, from line 1 to line 3. This is really what that number is in both places, but it's better to be writing all of the exact forms, right? So now I need to solve for x, and I have it in two places. Not if I factor out an x. Because if I get one singular x and I have this quantity here, which again is a number, it is like 0.139 or something like that. And I could divide it over. So going back up to the top, x is equal to log base 5 of 4 over 1 minus log base 5 of 4. That again is the exact form of the answer, but if I want a decimal, log base 5 of 4, so that would be that divided by 6.21. There are 3 ways of doing this. That was one of them. I could have done log base 4. You could try to check out what that would represent or how that would go. But, and I wonder if there's another question I could do this on, there is another way, which I will talk about at some point eventually. Let's see if I have another one here. Sure, I'll do it here. Alrighty. This might be the last one I do because I also got to upload this on YouTube and I need some time to do that. So that's all right if we have like one slide left. All right, so I'll hurry through. We're going to take the natural log of both sides, not the log base either of the pre-existing bases. That's because I can use the same log rule, 3x plus 1 ln of 2 equals parentheses x minus 2 ln of 3. Again, these are numbers. 3 ln of 2 comes from multiplying. I'm going to put the x in front. So I'm distributing here and here, and I'm distributing here and here. But the order, you do prefer to have x before everything else. I'll write this as 3x though, sorry. 3x ln of 2. That's just the normal order for writing ln. And then plus ln of 2 equals x ln of 3 minus 2 ln of 3. Again, I'm trying to get all the terms with an x in them to one side. 3x ln of 2 minus x ln of 3 equals negative ln of 2 minus 2 ln of 3. Yep. Factor out an x. 3 ln of 2 minus ln of 3 equals negative ln of 2 minus 2 ln of 3. And I can divide. Negative ln of 2 minus 2 ln of 3. Treat this kind of like you're doing algebra and you're keeping track of variable terms. But because all 4 of these things are numbers, all 4 of those terms in the expression that we have are numbers, then we can treat them as such. And it is an answer just as much. Negative ln of 2. Let's do a big parentheses. Negative ln of 2 minus 2 ln of 3 divided by 3 ln of 2 minus ln of 3. Negative 2.95. I hope that I haven't made a calculator error. And I apologize if I have. I recommend that you try to calculate exactly what I've written down. Type in the full expression. Just copy it, and you should get the same answer. I'm working with this calculator. I'm trying my best. You don't even know. I've been using the change of base formula because this calculator doesn't have a log base 2 or 5 button. So it's easy for me to make a mistake. I apologize if I did. But I think that's where I'm going to end. Thank you, people. I hope at least half the class watches this video. Could be the beginning of a great YouTube channel. Alrighty. I don't know how to pause. I don't even know how to stop recording. We'll leave this in. No edits. No script. Thank goodness it's recording still. I truly don't. Stop? Is there a... I don't want to turn it off. I'm going to go get Rami.
will like show it all.
Hey, Rami, I don't even know how to stop the recording. I'm done.
We'll start by showing all ones on the
I was like, you don't just turn it off, right?
No, there's a big red button.
I didn't look that close. Oh, look, a big red button.
Yeah.